Okay. All right, I think I've got new streaming software good to go. So I think it successfully recorded my class this morning, so we'll see how it goes today. Oh, yeah, let's make that go away. There we go. All right, so today we're going to be looking at a style of machine learning known as reinforcement learning. The motivation of reinforcement learning is to think about how can we enable some AI that is in an environment of some kind, learn from experience in that environment to live a better life, so to speak. So this is really, really different in flavor from what we've looked at so far. Here we're looking at learning in the context of an agent that has a way to perceive the world, takes actions in that world, and learns from that experience in some way. So when we try to think about what it means to be in a world, the structure that we classically use to look at this is a mathematical construct known as a Markov chain. For those of you that haven't seen a Markov chain before, and to some degree, it's really just going to be an abstraction here. We're not going to build them explicitly. But the idea of a Markov chain is that it is a directed, weighted graph with edges showing probabilities of state transitions. So what do we mean by this? Each of the nodes in this graph denotes being in what we would call a state, a certain discrete description of existing in a particular way. So, for instance, we might have a notion of state where, let me make this a little bigger, I am inside this room. And from here then, there are some actions that I might take. So one action I might take might be to stay put. And you know what, if I stay put, that's going to be an edge that just loops right back around to staying in the room. And you know what, we might even say that staying put makes it really, really likely that I'm going to stay in the room. You know, we might even call it a 100% chance, a probability of 1. So I'm going to put a 1.0 on this edge. But now, I might consider trying an action to walk out of the room. So, walk out with the goal of being in the hallway. That said, I might be really clumsy, and my chances of walking out of the room might not be 100%. So let's say I'm a sufficiently skilled walker that I've got about a 0.9 probability of exiting the room, and I've got a 0.1 of walk out, causing me to stay right where I started. If, for instance, I lack the ability to open a door, or what have you, or I just can't quite reach the handle, can't quite make it happen. So a Markov chain is a pretty interesting and appealing way of modeling how an agent would interact with an environment. One aspect of it that makes it appealing is that it's straightforward to imagine how we might create a Markov chain based on how an agent actively interacts with the environment. That is, from a given state, there are several actions the agent can take. We could imagine systematically instructing the agent to try each of those actions a number of different times, and based on the state that the agent enters after trying the actions, we could actually build a probabilistic model of how likely it is for the agent to achieve a certain result given that action. And that's what would be involved in building a Markov chain. And so this provides a really nice way of modeling an environment. In fact, learning from experience the consequences of certain actions in the environment. The trouble with just building a Markov chain is that it doesn't really have a notion of why an agent would choose a particular action, right? Why is it that an agent would choose to stay put or choose to go into the hallway? Those notions don't really exist within a Markov chain as such. We need some kind of extra means of incentivizing our agent to actually want to do something. A way we can think about this is to introduce a notion of a reward. That is, that the agent gets some kind of a payoff for being in a particular state. So that at least provides some incentive, some reason for the agent to behave. That's a big advantage. There's a pretty big disadvantage, though, and that disadvantage is that it makes this data structure a lot more complicated, because not only are we calculating probabilities of transitions into these different states, we're also trying to work out how much reward am I actually likely to get if I go into that state. It's a tricky idea, but nevertheless really appealing, right? If we have a notion of getting rewards, then using that notion of reward is a way in which we can incentivize the agent to learn about the environment with a goal of learning about what kinds of actions can I take that give me rewards, that make good things happen. So, an interesting approach to this problem, and by the way, the notion of reward over here is where the idea of reinforcement comes from. That is, it's what makes reinforcement learning is the idea that picking an action leads to certain rewards, and that picking the action repeatedly, leading to good rewards, reinforces that behavior and makes it desirable to select. So, in any event, yeah, it's fairly challenging to think about both estimating the probability of the transition as well as the accumulated reward from doing so. Part of what makes this challenging is the fact that the reward might not necessarily be achieved one state over. We might have several states to transition through before we hit a jackpot of some kind, right? And so part of what we need to do as well is come up with a notion of, if I go this way, I'm getting warmer and warmer and warmer until finally I'm getting somewhere that's going to be beneficial in some way. So that's the problem that we're trying to solve with reinforcement learning. So the solution to this problem I'm going to present is not the only reinforcement learning algorithm, but it's far and away the simplest one. And it's simple in the sense that not only is it straightforward to implement, it is also pretty clear how the different pieces fit together to enable learning to happen. Furthermore, although there are aspects of it that may seem oversimplified, there are some really creative things we can do to adapt this approach to solve many different kinds of reinforcement learning problems. So this approach I'm going to show you all today is called Q-learning. And Q-learning is a pretty popular reinforcement learning algorithm. My own acquaintanceship with Q-learning began when thinking about applying it to some problems with robots. And that said, where it's probably had the most dramatic success recently is when it has been used in concert with a deep neural network to master many common arcade games. It's also been used in conjunction with a deep network for Go. So Q-learning has proven to be pretty versatile and important for these kinds of domains. It has some limitations, make no mistake about it, and we'll talk about that as well. But it's a pretty interesting and influential algorithm and stereotypical of the category of reinforcement learning. So what's the big idea of Q-learning? The big idea of Q-learning is to build a model that's reminiscent of the Markov chain. However, in Q-learning, the edges are not annotated with probabilities. The big idea of Q-learning is to directly annotate the edges with expected rewards. So, in other words, we're not so much concerned with what state do I wind up in as a result of taking this action, so much as how much reward should I ultimately expect by taking this action. At the heart of Q-learning, then, is a two-dimensional array. And we can just call this Q to follow convention. But really, what the letter Q stands for is expected reward. So whenever you see Q, just think expected reward. So it's a two-dimensional array. So what are the dimensions? This array has one dimension representing a state and another dimension representing an action. So we can see immediately one of the important limitations of Q-learning, which is that the notion of state and the notion of action have to be integers. Now, this isn't the hugest limitation ever in the sense that we can readily envision how lots of different kinds of continuous spaces can be transformed to integers. Likewise, even continuous actions we can think of in discrete ways. Maybe we can mix them in various ways or what have you. But for this coming week, to keep things simple, we're just going to say discrete states coming in and most especially discrete actions going out. Okay. It follows, right? I mean, we could always increase the granularity, right? So just have larger and larger numbers of states and larger numbers of actions to imitate a continuous space. What might you all guess might be a disadvantage of doing that? Where would larger number of states and larger number of actions maybe be disadvantageous if this is representing expected rewards? It'll be slower, right? That is, these values are not given to us. We're going to have to learn them. And in order to learn them, our agent is going to have to explore its environment. And in that process of exploration, the more states and actions there are as options, the more exploring it's going to have to do before its behavior begins to converge to something reasonable. All of that said, part of what's fun about Q-learning is that learning need never end. It can always continue to update its estimated reward as it gains more experience in the environment. And that's something that's really fun about Q-learning. But still, I think you're going to find that these generally start off pretty stupid. So, the big idea then is somehow by getting out there and experiencing different states and trying different actions in those different states, our agent can learn to make good choices. So let's now start thinking about how the agent might learn to make good choices. So there are several parts to this formula for the Q-learning, and I'm going to try to take them fairly slowly so that each component makes sense as we gradually build it up. The first aspect is something that we looked at, whoops, didn't mean to do that, is something that we looked at with the self-organizing map. And that is the idea that we're going to try to balance what we've already learned against what we're now learning. That is, we're going to have a notion of a learning rate, which we'll call alpha, that starts as a large value and gradually becomes a smaller value. So, how is this learning rate typically defined? Here is one common approach. It's typical to try to define this learning rate so that it has asymptotic behavior. That is, because in Q learning, it never ends, it never stops, we don't ever want the learning rate to go to 0. We want it to asymptotically approach a certain plateau of being relatively low but still contributing to updates. So here's a formula that can produce this. So we have 1 over 1 plus T over C. So what are the different pieces of this formula? C over here is going to be some constant that you're just going to pick. This is one of the knobs you can use to control the behavior of Q learning. We're going to talk about the influence of it in just a moment. T refers to a time step. And the way I'm going to encourage you all to think about this is to, for each one of these state action cells in the Q learning table, keep a count of how often an update has happened at that cell. If you keep track of how often an update has happened at that cell, you can use that value for your time step. So if it hasn't been visited very much, that time step is going to be a relatively low value. Let's think about the implications of it. If my time step is a value like 1, then I'm going to have 1 over some constant in my denominator. That's going to give me a relatively large value for my learning rate. Let me illustrate what I mean. Let's try that again. All right. I was just trying to change to blue, and it just went all crazy on me. Let's imagine that t equals 1 and c equals 10. So in that case, we're going to have 1 over 1 plus 1/10, which is going to be very, very close to 1. Right. As time goes on, though, its behavior is going to change, right? So let's imagine what this looks like when t equals 5. So when t equals 5, we have 1 over 1 plus 5/10. Or in other words, you've got 1 over 1 plus a half. So that's 1 over 3/2. So you wind up with something more like 2/3. So it's still relatively aggressive, but it's really starting to preserve a lot more of the original. When t hits 10, we get 1 over 1 plus 1. We get a half. So in other words, this constant represents how many time steps do I have to go before I have a perfect balance between how much I'm retaining my old knowledge and how much I'm using my new knowledge. So if you make this constant a large number, it's going to tend to take a long time where it's willing to entertain new ideas more. As C gets smaller, it's going to try to converge more quickly on what it's trying to do. And so that's that formula right there that can help us determine a learning rate. Any questions so far? Yes?
In this particular example, we're using C as 10. is 10 like a generally usable number, or there's a standard number that most people use?
There's no standard number. I just totally made it up. And part of what you're going to do in the assignment is you're going to try different numbers here and experiment and see for the domain that I'll be giving you what works well. Yeah. Good. Other questions so far? Yeah, Dan.
Since you set this thing up as an array, it looks like the actions you can take would be dependent upon the state you were in.
We're going to go with the idea that no matter what state you're in, you've got the complete set of actions as a simplifying assumption.
Okay.
Yeah. You can always do every action in any state. Yeah. Yes?
Also, it looks like this Q is represented a two-dimensional array of like state index is like an X and action X is like Y.
Sort of, except that they don't really correspond to Euclidean axes.
Oh, so then what does it, like, why is this stored in Q state action? Like what's there and what it is in terms of number and the definition?
So, to some degree, it can be literally anything you want. So, you've gotten an agent in an environment, and you need to take that environment and break it into states. Let's say, for example, you're trying to have your agent learn to play Tetris. Well, your Tetris learning agent needs to have some way of decomposing every possible Tetris position into a discrete number of states. So here's one way you might do it. You might scan the very top row of Tetris and see what's the pattern of things being there. What's the pattern of occupancy or non-occupancy? And then the action choices involve the rotations of the tetromino as it comes down. Obviously, if it's reinforcement, if it's doing Q-learning on Tetris, it's going to need some computational resources. There are a lot of possible combinations there. Lots of states in action. So it's going to be playing millions upon millions of games to learn anything. That's one way you can think about it. Here's another way you can think about it. Let's imagine you've got a robot and you want it to learn to avoid hitting things. The state could involve possible values of its sonar. So for instance, you might say, if the sonar value is really big, it's in the state of nothing there. If the sonar value is intermediate, it might be in the state of object kind of close. The sonar is right in front of it, it might be in the state of danger. And if its bump sensors are being triggered, it might be in the state of crash. So for the domain, you just determine what are the possible states that make sense for this domain, and then you encode them in the table. So as long as you can find a way to turn any experience of the agent into an integer, then you can use Q-learning.
I guess sort of my confusion was when you're representing a Q table in form of a two-dimensional array that has an X and Y value.
Sure.
In that spot, in that location, why is it there? Is it a double number? Or
it'll be a double.
And then what does that double represent?
Expected reward. It's the expected reward for choosing to take that action in the given state.
Okay.
Yeah.
And a reward has like any sort of range
to whatever you invent. Whatever you invent.
Okay.
Right. So you can set the rewards at any range you want. Ultimately, the Q table will start converging on what it expects that payoff to be. There's no intrinsic mathematical reason why it has to be between 0 and 1, although sometimes people will do that. Just because it looks pretty, or what have you. Dan, do you have a question?
Maybe I was trying to think of your example where you're doing like the robots and sonar or whatever.
Yeah.
I mean, if your states were how close the sonar ticks are getting, I mean, would your actions be like left, right, back, forward or something?
Exactly.
And so, well, I guess it would learn that maybe going backwards is good. When you're getting close to something would be what you would hope it would learn?
For example, yeah.
Okay.
Yeah. I mean, and this is something that we'll learn as well, is sometimes getting it to Q-learn something might be more work than actually programming it. So it goes, and it's just a matter of first trying to grasp what about this environment is hard, and to what degree is it easier to set it loose to figure it out than to work it out ahead of time. It's like the great puzzle of when to use machine learning in general, actually. All right. Cool. Any other questions so far? All right. So let's think about what it means to update one of these cells then. So if I want to update Q of some state and some action, this then is going to be a linear combination of 1 minus my learning rate times the value already there, plus my learning rate multiplied by some kind of estimated reward. That's the basic structure of the formula. We're certainly, obviously, going to dive in heavily into how we're going to estimate a reward. But that's the basic structure of the update. So this represents the past reward estimates I had. And then this represents what am I really expecting to have now? Any questions so far? Yes?
Why did you say 1 minus learning rate on that first part of the formula and then set learning rate on the second part of the formula?
So this is the kind of incremental averaging we were talking about with the self-organizing map. That is, alpha is representing how are we balancing these two things. So if my alpha value is really big, like close to 1 minus that is a very small number, and it means I'm largely disregarding what I already know. If my alpha is really small, it means I'm relying more on what I really already know, 1 minus a small number being close to 1, and I'm making very little use of my future estimated reward based on what I've learned on this time cycle. So this is just how we're balancing them out. So we're now going to work out this notion of an estimated reward and then plug it back into this formula. So in thinking about the estimated reward, the first thing we might want to use is the actual reward. In other words, in the current state, there needs to be some reward function that's constantly giving out rewards, okay? So that reward function is a function of the state I'm in. What reward am I getting in that state? And in principle, right, I could just stop right there, right? I mean, the algorithm would certainly do something if I stopped right there, right? What is the something? What do you all think this would be learning if my total estimated reward is the reward I'm getting in the present state?
Don't go anywhere. Don't change.
Don't go anywhere. As long as it's like a positive value, right? Yeah.
Maybe, what does it mean to have reward of the state we're in? Because it looks like R is like some function of S.
Right,
and then
yes.
How do you compute it and how do you get the values from it?
You make it up.
Okay.
And it depends on the domain. So, right, so this algorithm is really abstract, and it has lots of pieces that we customize for the domain that we're interested in. So one of those pieces is, where does a state come from? Depends on your domain. Another piece is, where does a reward come from? Let's think about our robot. What kinds of ways would we want to reward a robot that we don't want hitting walls? Dang it! So one way we could reward the robot is the reward function might be a negative number if the robot's bump sensors are actively contacting something. You know, and otherwise the robot just meanders around. So, watch me do this again. Right? So, if my estimated reward is only coming from the reward in the current state, what is wrong with this algorithm?
You're doing the same thing.
I am. And why am I doing the same thing over and over again?
Because the steps preceding it aren't changing.
The steps preceding it are not changing, right? So we need to build in some kind of an idea of what happens in the future. And how does what happen in the future contribute to this estimated reward? In other words, we eventually want it to learn that, I'm getting kind of close. I'm getting closer. This is not good. This is better. I'm no longer going close to a wall, right? So, to be honest, I didn't actually kick it very hard. But the walls are really flimsy, and so it made a nice noise. Okay. So this really isn't enough, right? So what we're going to have to do is find out what's the Q value for the state that we wind up in after performing the action. And once we find out the Q value for the state we wind up in, we can incorporate that into this. So what would it mean to be able to do that? Well, part of what it means is ultimately, our algorithms are just as bad at knowing the future as we are. That is to say, completely incapable of it. So we're actually going to not be able to perform the update until after we've performed that action that then moves us to a new state or a potential new state. Because every time we perform an action, we have to find out from the environment, what state am I now in? So that state that results from it, we're going to call S prime. S prime. So here is a possibility that we could use. Would be to find out the maximum across all actions of Q S prime A. So what is this saying? It's saying we're now one step in the future. We're aware of the state we got into as a result of selecting that action. In that state, we can now contemplate all possible future actions. All possible future actions. And find what's the maximum reward I could expect given any of those actions. So the presumption here is that ultimately I will want to pick my action based on what gives me the biggest expected reward in that state. Right? Yes, innocently.
So, I'm thinking that what if taking that action might kind of give you a good reward, but an action that comes after it might lead you like in a very bad decision?
That's what this is trying to do, is to say, and part of the idea here is that ultimately our agent needs to have many visits to every state action pair. So our agent is going to have to repeatedly visit every state, and in every state our agent is going to have to repeatedly try every action over and over again. And over time, that should give us some belief that, if I know the expected reward for that future state, I can somehow balance it against this reward value here. Right? Yeah, Dan.
Do we know S prime is a function of S and A?
The environment tells us that. So in other words, I'm in state S, I have picked A. And then my environment tells me your new state is S prime after you did A. That's basically where it comes from. Yes?
Is it always the case that if you're in a state and you take an action, you end up in another state, or you might even come back to your original state?
Oh, you could be in the same state, right? So S prime could easily equal S.
Okay.
Right? There's no guarantee that there's a transition, and in the end, we're actually not even modeling it explicitly. That's part of the Q-learning shortcut, is the idea of saying, we don't have it's a lot of effort to model both the state transitions in the Markov chain as well as modeling the expected reward. So what we're going to do is just model the expected reward. And the probabilities of the state transition, in effect, are just all amalgamated together into this notion of this is my reward for doing this. Yes?
Okay, so I want to get a value for QSA.
Yeah,
I need to know an estimated reward.
that's right.
And in order to do that, I can easily run over all the possible A's with the max function.
Yep.
What are we going to put in for S prime? How do you calculate a value?
Before you're actually there?
Yeah.
Started at 0, and over time it should change, right? So that's really, really important, which is before you've got any future values, you really are just going on present reward, right? So you can imagine initializing the whole array to zeros. Positive numbers for good things, negative numbers for bad things, right? And initially, you're not getting anything from this term. So you're just kind of going on your present rewards. But after a number of iterations, what begins to happen is that thanks to having gotten some of these rewards, these values actually start to move away from 0. And once these start moving away from 0, these begin influencing the overall thing. Yeah, David.
So rewards is an array that you're checking with the states, not the actions. Like you have to own an array of or it's just one reward.
The reward is just the environment telling you this is what you get for doing this, for being in this state.
And you're only calculating that for
And that's instantaneous, right?
Yeah.
So every time you enter a state, it says, bam, here's your reward. Here's the payoff you got. Yeah. Yes?
So the rewards, like an example where you had like 4 different states for the
That's
robot.
right. Mm-hmm.
Would we have to know when we start this whole thing off before we train it that we're going to assign different values to each of those 4 states? Like bumping the wall is a -1 and getting close to a wall is maybe like -1/2 and being far away. Or does it determine values for those rewards on its own as it learns?
So the reward function is how any learning gets incentivized. So without the reward function coming externally, it has no way to learn anything. And you're not necessarily limited to the state encoding for determining the rewards. That said, if it's completely unrelated to the state encoding, it's sort of unfair to it, right? But you could work out what the reward should be based on aspects of it that you before you compress it into a state notation or whatever. It can really just be anything you want. So, if you think about the robot and hitting the walls, do you all think that a good reward would only be not hitting the walls, or would there be something else we might want it to do?
Not hitting the wall and
Say that again, Silas.
not hitting the wall and being able to move backwards.
Right. Not hitting the wall and being able to move. In other words, we would imagine that not only do we want the robot not hitting the wall, we also want the robot actually moving forward. It's pretty amusing to run that Q-learner without any reward for moving forward. What action do you think it would converge upon in that case?
Stays the same.
Sitting still, yeah. Either sitting still, or if you don't have a sitting still action, it'll just loop.
Spin around.
It'll learn that very, very fast. In every state, turn. It'll figure that out pretty quickly. Yeah. That's right. So you then want to build in a reward for, say, trying that going forward action. The fact that you're moving forward maybe is part of what gives you the reward. You don't necessarily incorporate that into the state. So the state might just be based on sonar distance, but then the reward might be based on he chose this action. Attaboy. Way to go forward. Yes?
Yeah, so this question I'm going to ask kind of ties back to the theme of the course.
Right.
We are learning how we can build like intelligent systems in which you can throw in like some data as training data,
Right.
and then use some test data for that system to make better action depending
Right.
on the test data. In the realms of Q-learning, what kind of training data are we using and how are we testing the system so if it's intelligent?
There's no training data. Right? There's just the reward function. Instead of training data, we have rewards. That's all. And it's trying to learn to maximize those rewards.
Okay, then how do we test its state of being intelligent for it to solve our intentions?
Right. You need to quantify your intentions and observe whether it follows them.
Okay.
Yeah. So, like, I knew some guys who I used to work for who, I spent the summer working with some NASA robot people, and they were using Q-learning for controlling the environment conditions in an enclosed habitat. So, in other words, there would be all kinds of state inputs about the people in the habitat and the temperature and waste products and what have you. And then it was learning actions to take based on the reward of healthy humans. Which again had to be quantitatively measured in some fashion. So that's another example of the kind of stuff you can do with this. So yeah, it really just kind of comes down to, actually it really comes down to this. Is it easier to program the system to meet your requirements by specifying a reward function and setting it loose with Q-learning, or is it easier to hand code the behaviors that you want? There's no a priori answer. Sometimes it's one, sometimes it's another. What really makes this interesting, of course, is how a reward function can encode these contradictory ideas. Like, my robot needs to keep moving forward. It needs to keep going forward. But it also needs to not hit stuff. Right now it's going forward, and it's about to hit something. There's conflict there. Right? And so where Q-learning shines is as a means of using the expected rewards to mediate the conflict when selecting an action. And that's where this really excels. So this formula is not quite complete. Let me talk a little bit about why. Let's say your rewards are positive, and it's really just about trying to get beyond zero, and maybe there's some small negatives in there. But let's say that your agent converges on a set of actions that it's continuously getting positive rewards. And as it keeps going, it keeps getting bigger and bigger positive rewards. This formula as it stands then has a little bit of a drawback because it will never actually converge, right? If it's constantly getting positive rewards going into the future and it finds itself in this state loop that keeps giving it those positive rewards, these values grow without limit. So we need to introduce another magic constant to try to slow that growth. That magic constant is usually represented by the Greek letter gamma, and this is known as the discount. This will be a value between 0 and 1. If your discount, yes, Jake?
Is that a minus or?
It's a multiplication, yeah. There we go. Is that a more filled in dot? So this discount is getting multiplied by that expected reward before it gets added to the present reward. And the goal is to keep the Q values from completely diverging to infinity. By having the value be below 1, at some point the values will actually have to converge. Because in effect, you're saying each action you take is being multiplied out by gamma. And so if you multiply an infinite number of gammas, which are between 0 and 1, of course it'll go down. The limit is 0. Right? And it never actually reaches 0, but the limit is 0. Right? And so by causing this term to have a finite limit, we enable the Q values to settle down over time. Yes?
So is this like a new term that we introduced?
Yeah, the discount.
Do you generate the value randomly, or we have a function that we throw in a number and give us back a number?
You make it up. Let's think about how we make it up. A low discount rate, like say 0.1. So a present reward is 10 times more valuable than a future reward. That tends to encourage very short-term behavior, right? Because we're prioritizing near-term rewards. Let's imagine a discount of 0.9. At 0.9, future rewards are almost perfectly balanced with present rewards. And so that's going to be a very forward-thinking agent that's going to be picking actions carefully to keep the future in mind. Yes?
But is this thing just looking one step in the future, or is this thing iteratively going out multiple steps in the future?
The answer is both. It's really just going one step in the future. But given that the thing it looked at in the future was calculated the same way, it too was looking one step in the future, and so ultimately it's getting a lot of future encoded in. That's part of the genius of Q learning, is to compress all of those future outcomes into a single expected reward number. And so this gamma parameter helps demonstrate to what degree are we balancing present versus future outcomes. Here's an analogy. Let's say a student has a major assignment due the next day. Let's say the student then decides to order a pizza and watch a movie on Netflix with some friends. That would be an example of somebody who's got a low discount number, right? On the other hand, the student who chooses to eschew the movie and focus on getting the work done, that reflects more of a high discount value. The future reward of getting the work done defeats the immediate reward associated with watching the movie. Yes?
Okay, we've got a Q of SA, and in order to calculate that value, we need to get an estimated reward,
Yeah.
which involves a Q S prime A. How does that ever terminate?
It doesn't. This never terminates.
So how do you ever get back to a value that you put in the matrix?
Oh, I see what you mean. Instantaneously, this terminates, right? And so the way that it terminates is just you pick your action, you apply it, you now have a future state, S prime, and you now update the previous state you were in based on going to the new state.
And you update it each time, so then when you go one more state, you go back and you update both of the previous ones?
No, you just update the last one because we're only ever looking at current state and future state. And we're really just looking at the chain reaction effect of all of these rewards have all possible futures wrapped up in them to actually get us to have a deeper appreciation of the model. That's the basic idea. Yes?
So you know how in the process of learning, we do some action, we get rewards or get punishment, we do the action, we get some punishment, and sometimes can be like 3 or 4 different action getting rewards, and then you get this one punishment, and you're like, I don't know taking up this 5 action that I did in the past. Because they owed it to this action, they gave me to be punished here. It sounds like our little robot is only learning to do things, then changing what it learned previously, now looking ahead about things that it is done in the history.
So part of what this is relying on is that we're taking multiple passes through the action selections.
Okay.
So, you know, let's imagine Pac-Man, right? So Pac-Man is getting rewarded for every Pac-Man dot that he eats. He's going reward, 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 goes, right? So the learner is going to take multiple passes through that experience. Eventually, Pac-Man is going to see, dang, there are 5 dots I can eat, but there's a ghost, I'm turning around. But for it to get to that point, Pac-Man is going to have to die an awful lot. So obviously, if you're using Q-learning, especially if you do it with a physical robot, you're going to have to make sure that when it gets its maximally negative reward, it's not actually destroyed. Otherwise, you know, it's expensive.
So this would be a terrible algorithm for a human to be running in their brain? And if they were doing this, this would be really bad?
Well, let's think about this for a bit, right? Unfortunately, you know, so there is an aspect of this that resembles what happens with us cognitively, right? We get rewards. We discount the future to some degree. We try to take the future into account, and so forth. Something that sometimes can happen is that someone chases a particular reward a little too strongly and, in fact, has a fatality, right? Think of the stereotype. You know, so as most of you all know, right, your car insurance rates plummet once you turn 25. They fall through the floor at 25. Why do they fall through the floor at 25? People 25 and over drive a lot more carefully. It turns out this actually has a basis in neuroscience, although the actuaries didn't really care about that, which is that the frontal lobe of the brain doesn't complete its formation until about the age of 25. And that frontal lobe helps inhibit poor choices of actions. So there's a stereotype grounded in reality of the 16-year-old who just got his driver's license, is driving like a maniac, and then gets into a nasty car crash. Well, Q-learning didn't help the poor guy. But something else we know is that experiences in practice have a very fine gradation of rewards in the human experience. We have many different thresholds of pain that we can experience. And as pain increases, suddenly this value starts dropping massively if we continue that given action to the point where we change, right? Think about touching a stove or something, right? Initially, oh, it's glowing red. That's cool. Ow! That hand isn't getting so close to the stove next time. I have updated my Q matrix. Now, obviously, this isn't modeling human behavior perfectly, and there's no pretense that it is. But it's a pretty concise, handy mathematical model of the idea of learning by reward. And there it is. So, let's restate the Q-learning update concisely now that we've derived it, right? So QSA equals 1 minus alpha QSA plus the reward that we experienced when we were in state S. Oh, whoops. Forgot a little term. I'm going to put this down here to make this easier to read. Plus alpha times the reward we experienced in state S plus gamma multiplied by max A in the state in the set of all actions Q of S prime A. And this is the Q learning update function right there. Just staring at it right, it looks like a lot of gobbledygook, which is why I tried to go through it very slowly to make sure that every component of it was as clear as possible in terms of the role that it plays in the algorithm. There's one extremely important aspect of the algorithm that we have not yet discussed, however, and that is a trade-off between what's called exploration versus exploitation. The nature of the trade-off is as follows. To derive good Q values, you have to repeatedly visit every state action pair. However, what we really want to do is kind of go with the best action, right? We're not really getting much benefit from this if we keep insisting on trying every state action pair. So exploration is the process of populating the Q table with enough values so that you've actually got enough data to make informed decisions. Exploitation is saying, yeah, I'm pretty world weary at this point. I kind of know what to expect. I am ready to excel, right? I'm going to pick the best action. So action selection for exploitation is very, very simple. If you're exploiting, you find, given the state you have now entered, which action gives me the biggest Q value. Bam, that's my action. Exploration, it's trickier. Here's an approach I'm going to suggest for this assignment. There are other approaches, but this approach is very straightforward. Have a target number of state action visits. So you just set that to be a constant like 10. How do you know what it is? Sorry, innocent, you make it up. You tweak it experimentally. You see where you get, right? Okay. So you have a target number of visits, okay? So if for all possible actions that target is met, we then go to exploitation. Otherwise, pick A with the fewest visits. Whichever action you've tried the least often in the given state is the action that you select. So this is fairly crude but effective. It's crude in that there isn't a particularly smooth trade-off between exploration and exploitation. You explore until you exploit. But in practice, it works out fairly well. If you figure out a good target number of visits such that you've got a pretty good idea of what's going to happen. And a lot of it, of course, depends on the size of the environment, the possible number of states you might have to go through, and everything associated with that, right? But once you work out that number, this works out fairly well. There are other approaches. Something that's pretty common is to do something like have a probability of exploring versus exploiting that depends on this number of visits, for instance. You could even have the probability be based on the learning rate. So the probability of exploring could be the learning rate itself. So early on, when your learning rate's really high, you're likely to explore. Later, you exploit. And when you explore, you can use this minimum visit approach. You can even just pick a random action. So those are also valid approaches to doing this. Yes?
So does the action of exploration and exploitation still happen in the same process of just like an agent operating in the environment?
Yep, this is all happening at once.
Oh, so let's say the agent is somewhere and calculating some reward system for the future, take an action.
Yeah.
The action might be an exploration action or an exploitation action,
That's right.
depending on how many times it has
Yep.
been taken before.
That's right.
Okay.
Yeah. Yeah. Note that even if exploration is over and exploitation begins, the action selection can ultimately change if the reward structure changes. So if something about the environment changes such that taking that action stops getting those good rewards, the Q values will actually begin to diminish. And it may then start to exploit a different action. So even at this stage, Q learning can still be fairly robust to the idea of the environment changing and being dynamic, which is something else that's really cool about this algorithm. I mean, overall, this is obviously a tremendously fun algorithm. Of course, now you're wondering, what's our assignment? And then you might be thinking, you know, he really liked that robot thing. I bet that's our assignment. And you'd be right. So let me show you the environment. So this is the environment. And there's this little spinner here that says OB or RBT. OB means obstacle, and RBT means robot. And it's all about what are you placing. So if I put RBT, that controls where the little red robot goes. Let's say I want to place some obstacles. Obstacles are little green circles, except when they're yellow.
Does the yellow one have any specific meaning?
Oh, yes.
Okay.
Yes. So I'm going to start a little basic avoider that I built. Oh, man, it hit. We're going to let it wander around. Oh, bummer, it hit something. All right, what do y'all think yellow means?
Move towards where it's projecting, like see
It's the
It
next
can
obstacle in line.
It can see it with its sonar. It's in bounds of its sonar cone. Yeah.
But it just doesn't care right now. There's nothing there.
Well, it's not very smart right now. Okay. So you can make a little map like this, and then you can save and open previously created maps. So I'm going to go ahead and stop this from running. Note that you're getting some stats down here. How many moves has it made? How many are forward? How many collisions does it have? But yeah, you can like open a previously created map. Oh, my poor robot is on top of an obstacle. I'm going to relocate my robot. There we go. And start off. So what you can do is create different maps, different configurations of obstacles, and see how that interacts with different possibilities, you know, as you work on developing your Q learner. You might be thinking it's addictive to look at, and you'd be right as well. So this one actually has a little bit of brains. Random controller. Okay, I hope nobody gets any seizures from there. So part of what we're going to do is we've got these two controllers as baselines for comparison. So there's the one that moves completely randomly, and then there's this one that's got some very basic behavior. So what does this basic one do? If it gets hit or it finds something within a range of 30, it goes left. Otherwise, it goes forward. So what you might be wondering is your task. Your task is first to implement Q-learning. And so I've got a skeletal implementation in place for you. The unit tests are a bit lacking. Actually, I'm hoping to put a few of those together for you and distribute them tomorrow. But the basic structure is here, and I've broken it into some functions that I think will be helpful. So here's the basic data structure. You've got a double array, two-dimensional array of doubles for Q, two-dimensional array of ints for your visits. You've got your number of target visits before you begin exploiting. You've got your discount rate, and then the rate constant for calculating that learning rate. And then you've got the last state that you're in, and the last action that you perform. So what you can do then is we've got this kind of a mega method here called sense act learn. So you tell it, this is your new state. This is the reward you got in the last state. So you'll calculate the update for the last state in action. You'll modify the Q value for the last state in action. You're going to pick the best action for the new state. Then you're going to change that last state and last action to be the new state and the action you've picked for it. And then you return the best action. And then I created some helper methods for you. Get learning rate. So find the total number of visits for the state to calculate the learning rate. Get the best action. And so there you're finding what action gives you the highest Q value. Is exploring returns true if there's any action that doesn't have enough visits, and then the least visited action. So those are some helper methods I used in my own implementation. Yes?
So when you say like return an action, are you returning any action array?
Yeah. So you're returning an integer index. Now, something I am not providing for you at all that you're going to have to code yourselves is once you've got the basic Q learning infrastructure in place, you have to use that to actually build a controller. So you can look at the basic avoider and the random controller to see how to interact with the simulator. And from there, you're going to have to come up with your own means of encoding sonar values and the like, and hits and so forth, and come up with your own state encodings. So you're going to basically build controllers that contain Q tables that then give actions. And they'll be just implementing this controller interface, which just has a simulator object, and the simulator you give instructions to and get data from. Yes?
Going back to the state and actions,
Yeah.
is that meaning that for the actions could be different for specific states because it's in the two-dimensional array?
Say that again?
That actions could be different for each state because it's in the two-dimensional array? Because if they're all the same actions, why would you need one for every single? Like are you like trying to associate? I don't know. I'm getting confused.
Oh, let me restate it then.
Yeah.
For every state, you're able to perform every possible action.
Yeah, I'm just wondering why it's part of the two-dimensional array.
So one dimension is what state I'm in. The other dimension is the action I'm taking. And the value is, this is the reward I expect for trying this action in this state.
Oh, okay, got it.
Yeah. Yes?
Is the state in this program the location XY axis, or is the state dependent upon what your sonar is getting?
It's all about how you encode the sonars.
Okay, so we get to define the state. That's part of the assignment.
That's part of the assignment, is to work out what's a state encoding that makes sense for this domain, that gives some nice trade-offs between being reachable, but also having enough granularity to give us some nice behavior. Yes?
Do you have access to parameters like sonar values, like maybe the distance that the
Yep.
explorers traveled, the number of obstacles in the environment?
So what you get comes from the simulator class. Obviously, within your controller, you shouldn't be using any imperative elements of the simulator, like adding objects to it. That was a design blunder on my part. So just don't exploit it. I mean, it would be pretty funny if you put those in as actions and you had it exploit things like adding objects and so forth. But In all seriousness, what you get is whether it's colliding with something, you can find the closest distance to anything, and that gives you the closer of the closest object and the closest edge. But if you want, you can also look directly at closest object and closest edge as well. That's basically what you got, yeah. Yes?
Is edge defined as the edge of the play space?
Yeah, exactly. Exactly. Yep. Yes?
Can you find the distance between yourself and an obstacle? Or-
That's what get closest object tells you. It gives you the distance between yourself and the closest object. Yes, Mitchell?
So there's no goal that
Well, you're going to encode that in the reward. Ultimately, the goal is to maximize your forward motion without hitting objects. Yes, Fish?
And by maximize our forward motion, do you mean there's a way for the little person to speed up? Or is it just take the most amount of steps?
We want it to prefer moving forward to turning. Yeah. It's going to go at a constant speed. Yeah. But we want it to really like going forward. And so when we think about the statistics you get in the simulator, the way you're going to talk about performance is to think about what proportion of my total moves were forward moves. You want that value to be as high as possible while not hitting things. Yes?
Well, when we were watching that thing go, it seemed a little weird as it would move closer to things. Dots that were really close, seemingly in front of it, would suddenly not be yellow anymore.
That's right. That's a feature, as it were, of how its sensor works. Its sonar is in a cone in front of it. And if it gets really close to something, it can enter its blind spot.
Okay, but we don't have any control over that, or we're not
Nope.
supposed to mess with that. We're just supposed to take what it sees as given
Yep.
by the way it's programmed.
Yep,
Okay.
that's right. Yeah. But yeah, so like that one
Yeah.
just entered its
Yeah.
blind spot. And then as it was about to hit it, it entered its blind spot because it just wasn't coming at it head on.
We know that one, that's blind spot, okay.
Actually, I'm wondering if this is buggy because it really ought to be turning before it hits. But I'll look at it later. So anyway, yeah, your goal is to see how much better can your Q learner do than these guys? How do the different Q learning parameters impact it and affect it? What can you learn about Q learning from this process? Yes?
just sorry.
Yeah.
Is there like a length of time we should run it for?
Just kind of a while. Yeah. Right, you might standardize on that. You might find, after it's gone for 10,000 time steps, that seems like a good limit, but I'm not specifying it ahead. Yes?
Okay, from what you're saying, you're disappointed right now that it's actually hitting the things before it turns.
Right.
Our goal would be to come up with settings for the parameters and everything so that it turns in advance of hitting things.
Yeah.
Okay.
Yeah. We really don't want collisions. Yeah. We're going to consider collisions undesirable. Yeah. It's going to go ouch whenever it hits an object. Something's, yeah. I'm going to have to double check that. Okay. Cool. But yeah, that is our reinforcement learning project. There's a fun overview of a really cool algorithm, and I'm looking forward to seeing what you all come up with. So we'll have our progress updates on Tuesday. By then, I'll be looking for, hopefully you've got your basic Q matrix implemented, and you've begun experimenting. You've got some idea of some parameters you've tried. Share some more stories, and then Thursday, we'll see where we're at. And then Thursday, it'll be submitted. You'll present the results. Note, clean slate going into spring break. Yes?
Where do we set the parameters in this thing? Is there some place like we're making new learners or something? Or?
Exactly, yeah. When you create your own classes that include the learner.
Okay.
Yeah. Yes, Fish?
Are we turning in a project proposal for our final project before or after spring break?
That is a great question. Let me see what my own calendar says.
I think before we'll be talking about that.
Oh, yeah. Final project. So we're going to turn it in after spring break. We're going to talk about them a week from today. Yeah. Thanks for bringing it up. And if I forget to talk about a week from today, yell at me. Yeah. Cool.
Of course, there's a tornado watch.
What's that?
There's a tornado watch for Faulkner County right now.
Sweet. Yeah.